Okay? So the sum of their gravity should equal 9.8. Okay, how about on this side? Their gravity also adds up, right? So the sum of them equals 9.8. Well, I think the same equation that's here is also the same equation that's here. Region 2 and region 3. Same equation should be able to give us both answers, because the difference is that their gravity is adding up. So then we're going to say C region 2 and 3. So then you're going to say G is equal to, it's pretty much going to be the same equation, 6.674 over 2.25. Times 10 to the minus 3 over x plus 1 squared plus 5 over x minus 3 squared. So now you see it's added instead of subtracted. And that's equal to 9.8. And again, it's going to give us two answers here. Negative 1.030, negative 1.03030 AU, which is not the same as the answer that you got. Let's see here. It's this one was probably slightly different. Looks like it's that. Let's see here. This one was negative 1.030132. And then that one is negative 1.030134. Oh, they're very close, but they're not the same. Negative 1.0304. And that's 1.00132. So they're not the same. So it can't be that they're the same, because this one is a minus and the other one is a plus. Okay, so then that's the answer on the left side. And then the other answer that it gives me, oh, it actually gives me four answers. It gives me negative 0.969, 2.961, but I'm going to reject those answers, because I'm going to reject any answer in between the two stars, because the gravitational field in between the stars adds up, doesn't subtract. So I'm only going to accept the one on the left side and on the right side. So 3.0389 AU. Okay, cool. So now I've got those locations. So then D says, what is the force that the two stars exert on the third star, whose mass is 4 times 10 to the 30 kilogram, placed at this location, given by the answers to C. Okay? So then how do we do that quickly? So then the force is just going to equal what? The mass of whatever you place there times the total gravitational field at that location. So you don't have to start this all the way from the beginning, right? So whatever mass, so we're just using F equals mg. This is the same equation that you use in physics 1 when you say W is mg. You say, okay, 80 kilogram person, how much do they weigh? Then you do 80 times 9.8, and it tells you how many newtons that person weighs, right? We do this in physics 1 all the time. Well, this is the same equation. So if I place a star at that location, its force on that will be its M times the total G there, which is 9.8. So then it's just going to be 4 times 10 to the 30 times 9.8. That's pretty fast. Okay, so 36, 3, 39.2, right? Times 10 to the 30 newtons. Or 3.92 times 10 to the 31 newtons. So that's it for that. Okay. The last question is having to find the total force on the star if it's placed at some random location. Okay. So that's as general as you can get. So now we're going to take that third star and put it at some random location. So now we have star A, star B. This one was at negative 1, 0 AU. This one was at 3, 0 AU. And then this one you're placing it where? 4, 2 did we say? 4, 2. Okay, so it's going to be around here. So star, we can call it star C. Okay, so then now each star will exert a force on there. This one will exert an attractive force. It's going to exert a pretty strong attractive force, right? And then this star will exert an attractive force towards it. We can say here this is FBC, FAC. Okay, and then the total force felt by that star is going to be the vector sum of the two, right? So now, just like with any vectors, to add them, you have to break them up into components, right? So then we're going to say F total X is FACX plus FBCX. And F total Y is FACY plus FBCY. So break this up into components here. So concentrate on this triangle for a second. So B, focus on that. B, C. This is F, B, C. Right, so this is the Y component, F, B, C, Y. This is the X component, F, B, C, X. And call this angle, let's say, alpha. So FBCX is going to be FBC sine alpha, right? FBC sine alpha. And then the Y is going to be FBC cosine alpha. Okay, and then so what's that going to be? Since the location of this was 4, 2 and the location of this was 3, 0, right? So this is actually 1 AU and this is 2 AU. And then the hypotenuse of that triangle, right? So this is 1 AU, 2 AU. The hypotenuse is square root of 5, right? So then you're going to have, if we're defining this as alpha, cosine of alpha is going to be 2 over square root of 5. And then sine of alpha is going to be 1 over square root of 5. So then you'll have here F total x is going to be FEC sine alpha 1 over square root of 5, and then FEC cosine is 2 over square root of 5. Okay, now let's do the FAC, and then that's this triangle. So this is still 2 with the bigger triangle, right? And then this one is going to be from -1 all the way to 4, so that's going to be 5, right? Yes, 5. So this is going to be 5 AU. So then this is going to be square root of 529. Okay, so now I'm going to define this angle as beta, right? And then this is going to be FAC cosine beta plus, and then this is going to be FAC sine beta plus, and then FAC, and sine beta is going to be sine beta is going to be 5 over square root of 29. This is where a lot of the trig comes in, right? And if you're shaky on that trig, you have to practice these kind of problems. Okay, and then this is going to be FAC cosine beta is going to be 2 over square root of 29. F total y. So right now all you're doing, all that we did was just do the trig portion of the problem. Now we're going to put in the law of gravity. So then we're going to say F total x is going to be FAC, which is 6.674 times 10 to the minus 11. Then that one I can factor out, and then that's the mass of star A, which is 3 times 10 to the 30th. Mass of star C, which is going to be what? 4 times 10 to the 30th. Divided by the distance squared, right? The distance, so is going to be FAC. So it's going to be this distance squared. So square root of 29 squared, which is just 29. Okay, but this is AUs, right? So square root of 29 squared. So then what do you have? Then you have to convert to meters. 1.5 times 10 to the 11th squared. Factor that out. Then you're going to multiply that by 5 over root 29. This one doesn't have units, so we don't need to worry about the meters. Why? Because the cosine of the angle is an AU over an AU, right? Because these are AUs here. Right, so the cosine of the angle or the sine of the angle, AU over AU cancels. So we don't have to worry about conversion to meters. They're unitless. So this portion, we don't worry about it. But this one, the distance squared, is where we convert to meters squared. You see. And then we add this to the mass of star B, which is 5 times 10 to the 30th. 4 times 10 to the 30th over square root of what? Square root of 5 squared. Square root of 5 squared times 1 over root 5. And then here's similar 6.674 times 10 to the minus 11 over 1.5 times 10 to the 11th squared, 3 times 10 to the 30th, 4 times 10 to the 30th, over square root of 29 squared. So here the only thing different is that instead of 5 over root 29, it's 2 over root 29. 2 over root 29 plus 30 times 10 to the 30th. No, 5 times 10 to the 30th. 4 times 10 to the 30th. Over square root of 5 squared times 2 over root 5. Okay, after this it's just a matter of now factoring out, simplifying. Now comes the algebra portion of it to do it correct. F total x is going to be, I can factor out, this one is going to be 10 to the 60th, 10 to the 60th, factor that out. To the 60th. Then I'm going to have here 3 times 4 is 12 over square root of 29 squared is going to be 29 times 5 over root 29 plus 20 over square root of 5 squared is 5, 1 over root 5. And then this is 10 to the 60th. And now the rest is just put this into the calculator and add them. 12 over 29 times 5 divided by 29 over 5. Plus 4 divided by 0.5. Now, why did I put a negative? Because this is, they're both to the left, right? The x. So actually this is just negative here, right? Because both the x directions of the forces were to the left, and both of them are down. So this is also negative. In case one of them was opposite, then you would have to account for one of them is to the right, one of them is to the left. But in our case, both of the forces are to the left, so you add them and you put a negative.
27.
Huh?
10 to 27.
Yeah, because this is going to be 10 to the 60th times 11, negative 11 is 10 to the 49, over 10 to the 22, 10 to the 27th. The rest just comes out to be some number.
Yeah.
And now the F total Y is also going to be probably 10 to the 27th. That's this one. Okay. Except you're going to have here 2 over root 29 and 2 over root 5, right? So the rest of it is going to be the same. So 12 divided by 29. Then I'm going to change that to 2. Then I'm going to change this one to 2 also. But this stays the same. So I'm getting negative 11.068 times 10 to the 27th. That means the y component is stronger. Understand? see. So this gives you the total force. So now if I wanted to know the magnitude and direction of that force, I can do the magnitude of that force is going to be then this squared plus this squared, right? 6.446 squared plus 11.068 squared square root. And then that's going to be the times 10 to the 27th. So this gives you magnitude and direction of the force. So you get the total magnitude by squaring the components, adding them, square rooting it. And then the phi, tangent of phi is going to be 11.068 over 6.446. Because remember, the forces were like this. This guy attracted it really strongly. That one attracted it a little weaker. So if you combine them, the net force is in that direction, right? So that means the net force felt by this is not directly towards here, it's slightly towards there, like that. So now the magnitude of this force, that's this guy. And then this phi is the angle of that force, right? So tangent of phi is the y over the x component. Okay, and then from there we can calculate the angle phi. So 11.068 divided by 6.446. Then tangent inverse (59.78 degrees below negative x-axis). Right? So that means the angle of the force, this is the negative x-axis, right? And so it's below the negative x-axis, and that's how much below it is. Now if that star had been in the middle between them, what would have likely happened? Let's say it had been somewhere here, then this guy would have attracted it. This guy would have attracted it, but not as strong. So then the vector sum of the two, it would have been like this. So that means the force would have been, I'm just guessing now, just guesstimating. You know, it would have been something like 80 degrees below x-axis. Now it's facing to the right, you see. What if the star is more closer to this guy? Then this guy might win. So the force might be really strong. The force of that might be weaker, right? Then when you add them, you get a force like this. You see? So now it might be maybe 65 degrees below x-axis. You see? So the vector sum of the forces is telling you the net force. So you can kind of tell, well, this guy is the heavier one, so it's going to win if I'm always closer to it. But if I'm closer to this guy has a chance of winning, right? So then you just do the sum of this force, sum of that force, then you get something like that, and you can say, okay, the total force is in this direction. You see, this problem actually, it becomes very complicated, and it's, I think it's an unsolved problem in physics. It's known as the three-body problem. Okay, the three-body problem, it says, what's the path taken by three objects who are gravitationally bound to each other? How do you solve? So they're going to be actually, all we're doing is mapping out the net force on one of the stars, right? But then these two stars will attract this guy. These two will attract this guy. And what's the path that they're going to take? Well, they're going to go around their common center of mass, wherever that center of mass is, right? In some complicated fashion. So how do you solve the path of that three-star system? You have to probably devise a computer program, right? With two stars, it's more doable, right? Two stars, make a line between them, and then their center of mass is the line adjoining the two. And then the two stars go around each other, and then their center of mass never changes, like that. So two-body problem is more solvable. Three-body is really hard. You have this one, and then you have a third one. And now try to say, this guy goes around here, but then the third one, right? And then four-body problem is even much harder, right? Four objects that are gravitationally bound, right? Now in our solar system, you almost have a problem, an issue like that. But since the sun's mass dominates over even Jupiter's mass, more or less the gravity that the planets feel from each other is negligible compared to the gravity they feel from the sun. So the sun dominates what is happening to each planet more than other planets dominate. Do you see the idea? But if the other planets also had masses similar to our sun, what would be the path that the Earth took? Or it would be a complicated path. You see? All the other, Jupiter would have a say in what we do. Saturn would have a say in what we do, you know. And then the path taken by all these objects would be so complex. That could be a good Physics 185 research, Louise.
Because it
Do the three-body problem.
Is it because it's four-dimensional stuff, you know?
Well, that you're even complicating it more. You're bringing in time and general relativity into it. I'm not even going there.
Yeah.
I'm just saying, and I'm not even bringing a third dimension necessarily. I'm saying, imagine that the plane was two dimensions. Even then, it's still hard.
Yeah.
But then you complicate it by bringing a third dimension, because maybe one planet is here, one planet is here, the other planet is below the plane. And so now, three dimensions is even harder. But now bring in general relativity and the fact that space is curved, and now bring in time as the fourth dimension, and now do the path of these guys. Only general relativity could explain the precession of the perihelion of Mercury. You know, even Mercury's path around the sun, just a two-body problem, was too complicated for Newton's law. Because